They use radar, satellites. What does it mean to you? Stay tuned as we explain the process of bringing home the weather.
For centuries, what we knew about our environment was simply what we could see and sense around us. Today's weather was easy enough to see. Tomorrow's weather in the hands of greater powers. Ben Franklin was one of the first to observe that storms travel across the surface of the Earth. That was in the 1700s. But not until the 1800s, the age of enterprise, would Mr. Franklin's observations be supported. The 19th century was a time of thinkers, tinkerers, a time when technology broke into all areas, and meteorologists drew their first weather maps. The maps gave the first clues as to the broad nature of weather systems. In the beginning, they were strictly research tools. This map was made using observations taken 3 p.m., August 11th, 1843, but it wasn't drawn until 1848. A map of the weather 5 years ago will not help with tomorrow's forecast. In order for these maps to be useful to a forecaster, someone had to find a way to collect current observations on a timely basis from a wide geographic area. That would take a modern communication network. So weather forecasting was born on the lines of the telegraph. In 1870, the Western Union Telegraph Company produced daily weather maps, charting temperature, wind direction, and cloud cover. That same year, because of a rising number of shipwrecks on the Great Lakes, President Ulysses S. Grant signed a resolution. It required the military to take meteorological observations and give warning to the approach of storms. In effect, a National Weather Service was started. It's been almost 120 years since President Grant's mandate for the taking of meteorological observations. I think he'd be quite pleased with the system we have in place today. We're here at the National Weather Service office in Athens, Georgia, housed in its local airport. It's one of 230 such offices around the country taking observations systematically throughout each and every day. Meteorologists like Greg Hansen record the hourly temperatures, the humidity. They check altimeters for the air pressure, eventually a visual state of the sky, the height of the cloud ceiling, any precipitation that has fallen. All of this information ends up in the hourly surface observations. The Weather Service codes and enters the information into a computer system which links Weather Service offices together. The computer transmits the message to the National Meteorological Center in Suitland, Maryland. Here, meteorologists plot those observations taken at the same time from all over the country. Now the process of making some sense out of all this data begins. One of the first steps in analyzing a map of observational data is to draw isobars on it. Iso meaning equal, bar for barometric, lines of equal barometric pressure. It's a lot like playing connecting the dots. The lines connect observations of equal barometric pressure. The pattern that emerges shows a kind of topographic map of the atmosphere. It shows peaks of high pressure and valleys of low pressure. On this map, the isobars encircle 3 areas of high pressure. But what is a high pressure system, and how does it form? Air masses get their physical properties from the land or water they are borne over. If air sits over very cold terrain, it cools, compresses, sinks. It will pile up until acted upon by forces of nature. It starts to move. The air within a high-pressure system is not stagnant. Imagine we are riding a gust of wind down this mass of air. If the Earth did not rotate, then we would merely slide down the dome, like water running down a hill. But our planet does rotate. So in the northern hemisphere where we live, our gust of wind is deflected to the right of the downward path. This is a law of nature known as the Coriolis effect. It causes the winds in a high-pressure system to rotate in a clockwise direction. Now, let's put our high-pressure system back on the map where we found it. The weather within the system is cold and clear, like this beautiful day in Denver. The three systems on our map have very different characteristics. The high in the southeast has picked up warm, moist air from the Gulf. The air mass to the north is cooler, but it has been weakened by a long trip across the continent. The boundaries where these three air masses collide are called fronts. If two air masses are of equal strength, then the boundary will be a stationary front, symbolized by a line with blue spikes and red rounded symbols. But on this particular day, the cold high was dominant, its pressure greater, so it developed a cold front. The blue spikes of the cold front indicate the direction it is moving. Cold air is moving in, pushing the warm air up. Meanwhile, the warm air mass is overtaking the cooler air to the north, resulting in a warm front. That's shown as a line with red rounded symbols facing the direction the front is moving. The warm air is riding up over the cooler air at the surface. At this point, the air circulation around the highs is developing a frontal wave, creating a low-pressure center. The wind circulation in the developing low is the opposite of the highs. It rotates counterclockwise. As the storm front matures, the cold front is usually moving faster than the warm front and starts to override the warm air. This stage is known as an occluded front. It is shown by this purple line of alternating spikes and rounded symbols on the same side of the front. Now that we have a better feel for how highs form, how the battle between the air masses develops fronts and lows, let's see how it all works together. Cold front wedges under the warm air and lifts it, forming clouds and precipitation. The steeper the lift, the more violent the weather. With the warm front, warm air replaces colder air on a more gradual slope. The clouds and precipitation may extend for hundreds of miles. Isobars, highs, lows, fronts, symbols on weather maps that you can see every day on TV. They can tell you a great deal about the weather now and what it will be in the future. When we come back, a bird's eye view from 22,000 miles away.
The GOES satellites provide an essential input to our nation's weather forecasters. Without GOES, we would be lost.
Enter the Drive-In, Drive-Out sweepstakes from Michelin and the Weather Channel, and you can win a new Jeep Cherokee or other great prizes. Enter at your participating Michelin dealer and get your free tire check while you're there.
Prior to the 1960s, most of the knowledge of the atmosphere was gathered through ground observations. Later on, pilot reports and weather balloons added depth to that perspective, but nothing like what was to come in the age of the rocket. In 1960, the Delta rocket gave NASA the ability to launch satellites. That same year, we saw our first pictures from a weather satellite.
First weather satellite was TIROS, Television Infrared Operational Satellite. It was launched in 1960, and immediately scientists on the ground who saw the images of the clouds from TIROS saw cloud formations that were theorized as to what they would look like from space. We immediately knew that this was going to be a real weather forecasting tool, not a research toy.
Today, satellites are the workhorses of weather forecasting. They provide the images that are so familiar on television weathercasts. We rely rely on two types of satellites for most of our weather information. One type, the polar orbiting satellites, pass over the poles of the Earth. On each pass, they view a swatch, 1,000 miles wide. Their orbits remain constant as the Earth rotates. So on each new pass, the satellite views a strip to the west of the one seen on the previous trip. Polar orbiters provide a detailed look at the atmosphere, but one we seldom see on television. What we do see are these broad views of the Earth provided by geostationary or GOES weather satellites. The GOES satellites consistently provide the same view of the Earth because they are in geosynchronous orbit, 23,400 miles above the equator. It takes the same amount of time for these satellites to orbit the Earth as it does for the Earth to rotate, 24 hours. The satellite stays in the same spot above the equator. The GOES system normally uses two satellites to cover the North American continent, GOES East and GOES West. The coverage overlaps and extends well into the surrounding oceans. There is a constant flow of information from the satellite sensing equipment to the ground and back. Different sensors are tuned to different types of radiation. This is a picture taken by GOES East using reflected light. The picture looks very much like an ordinary photograph. Tropical Storm Keith is in the Gulf of Mexico, and we can clearly see all of the broad-scale cloud patterns. But a reflected light image has its drawbacks. It is very difficult to distinguish high clouds from low clouds, and it cannot be taken at night. This is an infrared image of the same storm. The satellite uses a sensor tuned to the Earth's heat. An infrared image can be taken day or night. And an infrared image can also be enhanced by assigning color shades to different temperature values. Because high-altitude cloud tops are colder than low ones, the enhanced image tells us the heights of cloud tops. When this enhanced image was taken, a winter storm system was causing heavy weather from Minnesota to Texas. We can see a broad spectrum of color over Arkansas. The colors tell us not only the heights of the cloud tops, but what kind of weather might be going on there. The lighter colors at the bottom of the scale represent the warmest areas. This temperature range usually includes clouds that are close to the Earth's surface. So the outer rim of the storm system is made up of low-lying warmer clouds. As we move to the center, the temperature drops as the cloud tops reach higher and higher altitudes. This is significant because heavy weather, such as severe thunderstorms, can occur when clouds grow to higher altitudes. So by looking at this enhanced infrared image, we can tell that most of Arkansas is covered by high-altitude storm clouds. Clouds with the potential to produce severe weather. And that is just what happened. Severe thunderstorms exploded across the state. In Little Rock, low-lying areas of the city were flooded by torrential rains. 9 tornadoes ripped through the central and western areas of Arkansas. An image from space measuring the heat from clouds does not allow us to foresee this kind of tragedy. But satellite images do point out where the potential for severe weather exists. By adding the elements from a surface map, we can easily identify the major features of this weather system. The highs, centers of air masses, are typically found in clearer areas. The lows are in cloudy regions. Here, the comma-shaped clouds embedded in the low mark the major storm system. Fronts are often seen as bands of clouds. Here, the cold front dramatically depicts the collision of two air masses, the cold air to the west and the warm, moist air to the east. Satellite images and weather maps are two of the tools that help us bring the weather home to you. When we come back, tracking hurricanes and a vital satellite goes blind. Show the atmosphere as it really is, in constant motion. We can see the winter storm as it moves across the U.S., and we see the relationship of weather conditions across the country. The pieces of the atmospheric puzzle all fit together. The ability to see this motion makes satellite loops an ideal tool for tracking the deadliest storms on Earth. Forecasters here at the National Hurricane Center in Miami, Florida, used the images in September of 1988 to track one of the strongest hurricanes of the century, Hurricane Gilbert.
The disturbance that was later to become Hurricane Gilbert actually came off the coast of Africa on the 3rd of September as a tropical wave.
Bob Sheets is director of the National Hurricane Center.
It reached a tropical storm force late on the 9th, became a hurricane on the 10th of September as it was in the extreme eastern part of the Caribbean. As the hurricane was just south of Puerto Rico, about 30 hours before it moved across the eastern tip of Jamaica, hurricane warnings went up. So there was plenty of time for reaction in that island. Most of the people took the right actions.
Gilbert left Jamaica awash and destroyed homes and human suffering. But the only defense for those who lay in the path of a hurricane is advance warning. Jamaica had 30 hours to prepare for the worst. All along Gilbert's path of destruction, Haiti and finally Mexico, advance warning was given. The Hurricane Center uses a combination of airplane reconnaissance, computer forecast models, and satellite coverage to predict the paths of hurricanes.
If we only had one tool to observe the atmosphere, observe the hurricane, there is no question that any hurricane forecaster would take the GOES satellite. Not the polar orbiting satellite, but the GOES satellite, because of that continuous motion, the continuous observations that's available to us. And so many pieces of information are there. You not only see the hurricane itself, but you also see the environment. So it's our primary tool. 80 to 90% of our operation is based on satellite information here at the National Hurricane Center.
A major reason for the importance of satellites in hurricane coverage is the ability to see the storms in their infancy as they come off the coast of Africa. This is possible because of our two satellite coverage. GOES East covers the eastern part of our continent, as well as the Atlantic Ocean out to the tip of the African coast. GOES West covers the western continent as well as the Pacific Ocean, where our winter storms develop. But on January 21st of this year, GOES West ceased to transmit images.
Two things limit the lifetime of our satellites. One is the amount of fuel that we can launch along with a satellite, which it needs in order to keep it in exactly the right place throughout its lifetime. And the second is that electronic and mechanical parts do wear out. And in order to design them so that they wouldn't wear out, it would be prohibitive from a cost standpoint.
NOAA officials had anticipated the failure.
When GOES West failed, we immediately pulled out our contingency plans, which call for the movement of the eastern GOES to the center of the country. During the winter storm season, we will move the central GOES to a position slightly to the west, so we'll be able to see these storms a little bit farther out to the Pacific than afforded by a central position. During the hurricane season, we will be moving the central GOES now to a more eastward position to view the Caribbean better and the central Atlantic, where these storms form. The moving around will cost us a little fuel on board the central GOES. It takes about a pound of fuel to start the satellite moving and another pound to stop it, but we have plenty on board. As far as jeopardizing weather forecasting, again, we won't be able to see the Pacific storms until they're formed in the Central Pacific. We won't be able to see the Atlantic hurricanes until they're on top of the Caribbean.
With all the other data available to the Hurricane Center, will the one satellite system compromise hurricane coverage?
Indeed, there is a loss by not having that information out there. This year, we'll be compensated for that by getting more information from the European satellite. We'll try to get more of the polar orbiting data. Good, precise kind of information, but limited in terms of your coverage in time and space. We're concerned. I think that anyone who is involved in tropical meteorology is concerned. GOES is ideally suited for tropical meteorology. Indeed, it's very vital to provide the kind of service that we provide today. Next year, it's one satellite, and hopefully that one satellite will last through the end of the period till we get the new GOES next generation satellites.
The new GOES system is being built by Ford Aerospace here at their Space Systems Division in Palo Alto, California. It is scheduled for launch in 1990. Until then, we'll be operating with only one GOES satellite.
We are committed to having a launch in July of 1990, and the pressure is on to launch this satellite in order to have the two-satellite operational scenario. And we are on target. We will be able to meet that launch date. There's one thing that neither NASA nor NOAA can afford to do, and that is to have a break in service prior to the launch of Bullseye.
The first new GOES satellite is already being assembled in what is called the High Bay area. It is a dust-free environment. Once the satellite is completely built, it will undergo a rigorous series of tests, even to the point of simulating the space environment.
The main difficulty is associated with the lack of the ability to make adjustments after launch. In all your ground-type equipment, you can make adjustments. There's a warranty period, and during the warranty period, many corrections could be made by the manufacturer. In our case, we do not have that opportunity, and so we have to be especially careful, very thorough in our design, in our testing, our analyses, in order to try to cover all of the potential problems that might occur.
The new GOES system will consist of 10 satellites and will incorporate advances in both spacecraft and sensing technology.
Our new series of GOES satellites will be significantly better than the present ones. They'll be able to take more pictures, and they'll be able to take them faster to provide better information for forecasters to track severe storms. The pictures that are taken will be more accurate. We'll be able to tell exactly where the clouds are, and from that be able to predict more exactly where the weather systems are moving.
These satellites will take us beyond the year 2000, but before that, yet another generation of satellites will have to be developed. While satellite technology advances into the next century, another scientific revolution is going on right here on the ground. Next, Doppler radar, wind profilers, and how they will change the way we bring home the weather.
We know
Drive-out sweepstakes from Michelin and the Weather Channel, and you can win a new Jeep Cherokee or other great prizes. Enter at your participating Michelin dealer and get your free tire check while you're there.
No matter where you live, no matter how remote an area, chances are somebody's monitoring your weather with a weather radar. That's because there is a network of over 100 local radars across America that can detect precipitation from as far away as 200 miles. Because of that density, most of the country is covered by radar. Weather radar operates very much like radio in that it transmits and receives radio signals. The difference is that the transmitter and the receiver are in the same location. The radar sends out a beam of radiation that has been calibrated to reflect off particles the size of raindrops, snowflakes, or hailstones. When it hits this precipitation, it is reflected back toward the transmitter. This return signal, or echo, shows the radar operator the distance and the strength of the precipitation. In the field, the echoes on a radar scope are not easy to interpret. So for television, radar presentations have been digitized and enhanced. This is done by assigning different shades of gray or color to different levels of echo brightness. For example, this radar has been enhanced to show light rain as a light green color. Moderate rain is darker green. The yellow and orange areas are heavy precipitation, the kind you might find in thunderstorms. With the addition of map grids, you can see where the precipitation is falling in relationship to where you live. Here is a radar for Fargo, North Dakota. The area is receiving a fair amount of precipitation. If you look closely, you'll notice that the echo is a little bit fuzzy. The edges are softer. Most of the area is a light bluish green, indicating a light intensity of precipitation. This is showing snow. The echoes for snow are generally a bit softer than for rain because snowflakes reflect the signal back differently. You can see how much more defined are the echoes east of Kansas City, Missouri. You can make out bands or lines of multicolored, sharp-edged images. This is the stronger radar return of bands of rain showers. These showers moved through the Kansas City area earlier. And as the radar showed, they were light to moderate and have since moved into central Missouri. But look over Kansas City. We see echoes when we know the rain has moved on. These are false echoes or ground clutter. It results when the radar signal bounces off nearby buildings, trees, or mountains. What you are seeing is a mosaic of the terrain near the site. Another drawback of radar is that although the beam curves somewhat, it's not as much as the curvature of the Earth. So the beam can occasionally overshoot the tops of lower precipitating clouds, while covering higher clouds further away. Radar can also be used to show the movement of a storm. This radar shows the same storm over Little Rock, Arkansas that we have already analyzed using satellite images. By taking a rapid progression of radars, we can see the heavy rains generated by the thunderstorms as they move through. A composite of all the local radars at the time of the storm shows the enormous cold front generating heavy rains and severe weather down the length of the country. A national radar summary can be collected once an hour from weather surface radars around the country. The value of local radar is its timeliness. It shows the forecaster what is happening in his area now, crucial information when violent weather threatens. And if the potential for severe thunderstorms exists, then local radar becomes a tool for a group of specialized forecasters in Kansas City, Missouri. Kansas City is the home of the National Severe Storms Forecast Center.
At the Severe Storms Forecast Center, our primary mission is to monitor the weather over the entire United States and look for the conditions that are going to spawn areas of severe weather. By that we mean tornadoes or severe thunderstorms, and try to anticipate that, and when we find those kind of areas, issue a tornado or a severe thunderstorm watch, whichever is appropriate.
The job of monitoring the entire country falls to 4 meteorologists back here in the Severe Local Storms Unit. They use a system called CSIS for Centralized Satellite Information Services, developed specifically for specialized forecasting. The afternoon we were there, a cold front was moving through the southeastern United States. The clash of cold and warm air was causing unstable conditions above the Louisiana coast. Bob Johns checked for the conditions that would cause a turn for the worse. He first looked at the surface observations, checking for temperature contrast. He then surveys the areas where moisture is coming together, converging moisture which could be lifted higher into thunderstorms. Next, he checks for any instability in the atmosphere. Any of these occurring as an isolated condition would have little impact on a storm in progress, but where they all come together, a storm could turn dangerous.
In Alabama. So the two values of convergence of the winds coming together to make the air lift and the instability are closest together right in this area, and here's the gradient. So this is where we focus on. The values are fairly strong today, so we think there's going to be severe storms. Now once we've done that, in order to exactly lay out the watch, we'll go to the radar closest by, and here's out of Lake Charles, Louisiana, and we see there's the line of thunderstorms extending from Baton Rouge southward.
A box is placed on the map, outlining the area of potential, where the conditions are right, and the storm is on its way.
Okay, now that lines up just east of the line here. By the time the watch is valid, the line will be moving into the west side of it. We can get the new coordinates from this watch that we're finished up with here, take those coordinates, enter them into our computer here, and within a minute they're out to the weather service offices and the media.
Over 100,000 storms occur every year in the U.S. The Severe Storm Center monitors a great many of them, all in an effort to identify areas where pounding hail, floods, and tornadoes could strike. Coming up, Doppler radar and forecasting tornadoes.
You will be
Out of the 100,000 thunderstorms that occur yearly, only 10,000 produce severe weather. Out of these, only 1,000 produce tornadoes.
most of the tornadoes that occur in the United States are small and not very significant. So maybe you might have 25 tornadoes all year long that are significant. So our job is to try to anticipate the kind of the conditions from these 100,000 thunderstorms that occur all year long, which are going to be the ones that are going to give us these 25 possible killer tornadoes, and to get a timely watch
from our office, and then followed up by a timely warning at the local level.
A timely warning for one of nature's most violent phenomena is very difficult to accomplish. In the early morning hours of November 28, 1988, several tornadoes ripped through a 5-county area of North Carolina. There was no warning. In Raleigh-Durham, many awoke to rubble. The initial death toll stood at 5, with over 150 injured. In all, the twisters of that night caused an estimated $25 million in damage. Most people's first warning was the sound of the storm. Severe storms present a tough problem for the forecaster.
At present time, we do not hit the vast majority of those warnings. As a matter of fact, we are able to predict with warnings less than 2/3 of the actual severe storms and tornado events. And when we predict a severe storm or predict a tornado, we're wrong almost 2/3 of the time. We cry wolf almost 2/3 of the time.
But Doppler radar, the foundation for a new generation of Weather Service radar, may change the way we see storms develop. The radar is in use in Norman, Oklahoma, and the hope is that it will be in place nationally by the mid-1990s.
The current weather radars are able to detect clouds and identify moisture in the clouds, the cloud droplets. The new systems that will be coming on board are called Doppler weather radars, and they will detect not only the clouds themselves, but they will be able to detect the motion of the water droplets inside those clouds. Now, for those of us who were raised in the middle part of the country in Tornado Alley, that's very important, because you will be able to look inside the thunderstorms and to identify the motion occurring inside the thunderstorms and actually see the beginning of the tornado prior to its actual development. As far as the National Weather Service is concerned, we will have a much better outlook and a much better understanding on the development of severe weather.
Thunderstorms, tornadoes, they happen fast. Forecasters need information that can be updated as rapidly as the storms develop. A NOAA forecast research group in Boulder, Colorado, is focused on the problem. Their answer, the PROFS computerized workstation. PROFS for Program for Regional Observing and Forecasting Services.
The real strength in us is that the PROFS workstation is able to essentially gather quite a bit of different types of data very rapidly and display them for use by the forecasters.
John McGinley, Forecast Group Chief, explains how PROFS and Doppler radar were used successfully to predict a severe thunderstorm before it developed over Denver.
And what you're looking at here are actual air velocities, not the storms themselves, but how air is either moving away from or towards the radar. The yellow-brown shades here is air moving away from the radar. Here, the green shades is air moving towards the radar. So what you see here, essentially, as we step through this display, is watching the air moving away, merging with the air coming towards. So what that means is the air is two different air masses are smashing together, to use a very simple terminology, and that smashing together then produces thunderstorms in this area. We knew storms were going to develop because we saw the convergence probably half an hour to 45 minutes ahead of time.
These severe thunderstorms spawned 2 tornadoes. Both touched down within the Denver city limits.
The radar cannot detect motion across the radial in either direction, but it can detect motion both towards and away. So that signature of outbound and inbound velocities very close together tell us that there's rotation in the clouds in this vicinity, and it's an area, suspicious area to watch for tornadoes. And you can see here's the Denver metro area, and so that area of rotation can be positioned very accurately for warning purposes. Without the Doppler radar, without the PROFS workstation, this would have been a very hard event to diagnose.
Using Doppler and PROFS, tornado warnings were issued 15 minutes before the first twister touched down. About an hour's drive northeast of Boulder, the state of Colorado flattens into a plain. Out here, Doppler radar is being used to watch the wind. This flat grid is an antenna for a wind profiler. NOAA plans to place a demonstration network of Doppler wind profilers across the Midwest. Doug Vandekamp is involved with the program.
So Doug, explain what we have here with the wind profiler.
Well, this is the antenna for the radar wind profiler. Essentially, the energy comes out in cables underneath the antenna, and the energy comes up inside these tubes, which the actual antenna is located inside here. It's essentially a Doppler radar that sits on the ground looking nearly vertically and measures atmospheric motion above the radar site. We transmit a pulse of energy from the ground, from the antenna, and this radiates up into the atmosphere in a beam, and the beam intersects turbulence that's moving through the atmosphere, and this turbulence essentially causes the energy to reflect back to us. So by measuring the Doppler shift of that turbulence as it's moving through the air, we can measure what the winds are.
The wind profiler measures wind speeds and directions at different levels in the atmosphere. It is a clear air radar. No precipitation is needed to bounce its signal off of. The upper atmosphere is dynamic and complicated. We need current information on changes in the vertical if we want to be able to forecast rapidly evolving weather conditions. You're hearing the sound of another profiler. The Radioacoustic sounding system takes temperature profiles of the atmosphere, up to 6,000 feet. A sound signal is sent up into the sky. Doppler radar is then used to measure the speed of that sound. It's actually quite deafening.
There's a principle in acoustics that says the velocity of sound is directly proportional to the temperature in the atmosphere.
By knowing the speed of the sound, electronics engineer Ken Moran can tell the temperature of the air the signal is moving through.
On a day like today, when there's obviously some changes in the weather, it becomes very interesting to run a temperature profiler like this, because you can see structures in the atmosphere that are important to the changes that are taking place on the ground.
And will this information be any different from what is gathered from balloon launches?
A standard balloon is used for temperature profiles twice a day by most Weather Service offices, but that only gives them a short, quick look in the atmosphere. A system like this can measure temperatures every 5 or 6 minutes and give you the dynamics of the atmosphere as they take place.
Accurate information about weather conditions occurring now is the strength of radar. Whether it is telling us where the precipitation is falling or the temperature at 6,000 feet, radar has and will continue to play a large role in short-term weather forecasting. Next, from balloons to 10-day forecasts, together so we can bring home the weather.
Ready?
Presents a new puzzle to be solved by forecasters. Now, the pieces to this puzzle are provided by observations taken worldwide. Exactly at 0 and 12 Zulu, or more commonly referred to as noon and midnight, Greenwich Mean Time, weather balloons are launched around the globe. All of this is part of one of the most sophisticated sensing systems on this planet. The balloons go up from 700 sites worldwide, including this launch building in Athens, Georgia. Filled with hydrogen, the balloon will reach a height of 100,000 feet before bursting. Greg Hansen prepares the balloon for launch. The long lines are going to be used to tie an instrument package to the balloon. The package is called a radiosonde. It houses instruments that will measure pressure, temperature, and humidity at different levels on its trip up through the atmosphere.
Okay, we're ready for release.
The radiosonde is battery-powered and contains a transmitter. As its name suggests, the radiosonde will transmit radio signals, communicating the atmospheric conditions back to a receiver on the ground.
You ready?
Ready.
For about 45 minutes, the balloon will rise higher and higher. When it finally bursts, the radiosonde will fall back to Earth using a parachute. Hopefully, it will be found and returned to the Weather Service.
Okay, it's 09 and 55.
Greg shouts the coordinates of the rising balloon to an associate over a two-way intercom, who then fine-tunes the receiver. Because balloons are released at the same time around the world, the combined information gives us an instant global snapshot of the atmosphere. Contained within the radiosonde signal is a decipherable message, but the trip from balloon to receiver is just the beginning of a long electronic journey. The data enters an electronic pipeline that links the entire world. It joins tens of thousands of observations taken systematically around the globe. An enormous amount of computer power is used to compile the information. In the United States, all of this information merges at the National Meteorological Center in Suitland, Maryland.
Every major country throughout the world has a center something like this as part of its weather service that collects observations from around the world, usually runs those observations into large computers, analyzes the weather, and makes general weather forecasts of what the highs and lows and jet streams are going to do. Altogether, probably about 50,000 observations a day that come into the center. What comes out is something that's much more processed than that. What we turn out are analyses of what the weather is at the present time. Those would look like the charts that the Weather Channel shows, surface charts, upper air charts, where the fronts are, the highs and the lows. Then probably our most important product is a set of forecasts on what those weather maps are going to look like for the next day and the next day and on out as far as 10 days in advance.
The accuracy of these forecasts falls off at about 6 days. Still quite amazing. To arrive at this forecast, a computer must solve 7 very complicated equations at 18 different levels in the atmosphere. But computers have not replaced the expertise of the forecaster. Because of the vast amounts of information available here, the National Meteorological Center is able to provide a variety of forecast products. One of the more urgent is the heavy precipitation forecast. Here, forecasters monitor the country for areas where heavy rain or snowfall might occur, potential areas for floods. The day we were there, Tropical Storm Keith threatened northern Florida.
It's shearing out. Obviously, with any tropical system, there's a very high potential for some heavy rainfall, and that's our problem again tonight in northern Florida. Our main function is to provide guidance to the field forecasters so that when they put out their forecast, they have their own ideas, they have our ideas, and hopefully it's a combination of both to put out the best forecast available.
And it's to help either the private forecasters and the National Weather Service forecast centers, which are scattered around the country, to guide them in issuing flash flood watches for hydrologists to help them determine river rises and falls.
3 principal forecasts are issued: a 6-hour forecast, a long-range 24-hour forecast, and an excessive rainfall outlook. This continues throughout the life of the storm.
Our big problem with the tropical storm is to determine exactly where it's moving and how fast it's moving. We think it's going to be moving fast enough that there won't be any real serious problems, but maybe some 2 to 4 inch amounts that would maybe cause some local urban type flooding.
Once completed, a forecast is entered into the AFOS system. Within seconds, it can be called up on screens in Florida. Tropical Storm Keith made landfall on November 23, 1988 at around 2 a.m. The storm's heavy rains caused the expected street flooding in northern and central Florida. Knowing where heavy rain is likely to fall is very important. Flash floods kill more people than any other weather phenomena. Through AFOS, a tremendous amount of data flows from the National Meteorological Center to local weather service offices, like this one in Washington, D.C. Here, Jim Belleville is using the long-range forecast to decide what effects Tropical Storm Keith will have on their local weather in the days to come. He begins with the 2-day forecast.
We could expect showers to occur in through southern Virginia, which is exactly what's in the forecast. If we go ahead another 24 hours, we find that the system has moved from the Florida Panhandle out into the Atlantic Ocean, several hundred miles east of the United States mainland, right into this area here. What this indicates is that the counterclockwise flow around the low will actually bring cool, dry air down into the area. Indicates cool and dry weather over the most of the eastern United States.
The forecast proved to be accurate for Washington, D.C. and the surrounding area. 10 years ago, a reliable 5-day forecast would have been impossible. Today, we stand on the threshold of a new age in meteorology.
With all
of the new technology and the new ways of observing the atmosphere being developed now and coming along over the next 5 or 6 years across this country. With the new radars, the new satellites that you've discussed earlier, the ability to bring all of these data together with an interactive computer system so that the forecaster has at his or her immediate access all of the information that there is describing the atmosphere and the best projections from the computer models as to what that atmosphere is going to do. I think in 10 years you're going to see the 7-day forecast or maybe even the 10-day forecast as good as our 5-day forecast are today, so that you can start to reliably bank on what's going to happen over this entire next week. I think what you'll see, more accurate forecast, more reliable forecast, and forecast that we can stand behind very well.
The atmosphere's chaotic behavior makes it one of the most complex physics problems facing science, and yet our ability to predict the weather continues to improve. By understanding the maps, the echoes, and the images used in television weathercast, you can take full advantage of the technological revolution that will be changing the way meteorologists and forecasters are bringing home the weather. For the Weather Channel, I'm Dennis Smith.
Destruction firsthand and live to tell about it.